Right. So my project this year seeks to address the opioid crisis. So as I'm sure many of you have heard, the opioid epidemic has been a major problem for communities around the world for decades now. Now, the problem with some current approaches is that they are very reliant on lab-based equipment, such as the high-resolution mass spectrometer. Now, my project tested one specific opioid substance in general, oxycodone, an extremely potent and commonly abused opioid. We also used a silver-doped zinc oxide nanoarray for the extreme enhancement of our detection. And the main method that we used to detect our opioid substance was a technique called Raman spectroscopy, which in essence allows us to create a molecular fingerprint that is unique to each molecular compound. And the way we do that is we stimulate the molecule via a laser, and its unique bond and electron configuration will scatter the light in a way that is unique only to that substance. However, the problem is that without any sort of enhancement, the signal is very, very weak. As you can see here, it's only an indistinguishable percentage of all the light that's scattered. So we added a plasmonic material, specifically silver, which has the best performance on our detection substrate, which significantly enhanced the signal. And here you can see this is a rendering of our procedure. We first seeded a bare silicon wafer with the precursors to the zinc oxide nanorods, and then we use a hydrothermal deposition growth method to grow the rods vertically and in parallel to create an almost forest-like structure. And then we use that as a scaffolding to decorate silver on top of it, which serves as the main component for amplification. The results were very promising. As you can see here, the detection peaks are at around a Raman shift of 1400 and 1600, which are labeled for your convenience. And the signal actually scales with the concentration of the opioids in the water. As you can see here, the curve for 0.5 milligrams per milliliter is significantly higher than the detection curve for 0.001 milligrams per milliliter. And our sensor limit is actually at 0.1 micrograms per milliliter, which is shown here. Despite its seemingly flatter peak, this is only because it is smaller in contrast to the much higher magnitudes. However, here you can see there are still significant detection peaks here at 1400 and 1600 compared to a baseline graph. So in conclusion, we could reliably detect the presence and concentration of oxycodone, which is only one of several types of opioids we could potentially detect. And the peaks appear to be smaller, but they are still very significant at our sensor limit. As you can see here, they are still very detectable, which proves that our sensor can indeed reach this detection limit of around 0.1 micrograms per milliliter, which is 1,000 times better than the current existing portable detection method. And our method is very portable and label-free, which serves for a very effective on-chip point-of-care method for opioid detection that could potentially be used across America and around the world to map out the opioid crisis and provide a reliable way for providing point-of-care solutions for communities. Thank you.